In this video, we're going to prove a very important theorem. It turns out that if you have a vector space for V that has n vectors in it, and T has a linearly independent set of k vectors in V, then k must be less than n. You can't, if a vector space has n elements, you cannot come up with more than n elements or n vectors of a set and that set be linearly independent. You can never have more than n linearly independent vectors for a vector space V if you can find a basis with n elements. Now we're going to prove this, I guess, by contradiction. Suppose that k is bigger than n. Now consider this set. Define set 1, R1, to equal to S, V1, V2, all the way up to Vn, but including W1. Okay, this is a linearly, this spans V. Why does this span V? Because that's the basis for V, and you can find for given any vector in V, you can find a linear combination of those vectors that will give you V. For example, if V is equal to C1 V1 plus C2 V2 all the way up to Cn Vn, and you say, hey, you didn't include W1. You're right. How about 0 times W1 plus C1 V1 plus C2 V2 all the way up to Cn Vn. Just for the record, if I change that, that can also be non-zero, but then those CIs will be different than these CIs. But just because you add a vector to a basis, that new vector set will still span V. Okay. Now, since these vectors span V, okay, let's write that. Since S spans V, we can write W1 to be a linear combination of the vectors in V. The vectors in S. Now, since T, and this vector is in T, since T is a linearly independent set, it can't have the 0 vector. Why can't it have the 0 vector? If T was equal to 0, W1, W2 up to WK. So if I took a linear combination of these vectors, well, let's just say W1 was 0. If I took a linear combination of those vectors that equals 0, I can do 0 times W1 plus, 20 times W1 plus 0 times W2 plus 0 times W3 all the way up to 0 times WK. And there's a problem. This set must be dependent. Why? Because I found a linear combination of W1, W2, W3, WK, that is the vectors in T, and that equals 0, and not all of the coefficients were 0. That number is not 0. So you can never have a 0 vector in a linearly independent set. Maybe if this set just contains the 0 vector, I don't know. You have to think about that. Okay, so now W1 can be written as this, but this is not 0. W1 is not 0. So this mess does not equal 0. That implies that at least, now, okay, let me just state it. At least one CI is not 0. Why? Because if all the CIs were 0, you have 0 times V1 plus 0 times V2, excuse me, all the way down to 0 times Vn. Well, that's 0, and that's 0, and that's 0, and all of those are zeros. You add them up, you get 0. But that would contradict that it's not 0. So you can have all the CIs equal to 0. Without loss of generality, assume C1 is not 0. That means that I can solve this equation for V1. For right now, I'll solve for C1 V1. It equals to the left-hand side, W1, and then bring everything else over to the left side. Or 1 times W1 minus C1 V1 minus C2 V2, all the way down to C sub n V sub n. And then I divide by C1. I divide by C1. And what I notice is that I can write C1 as the linear combination of, that should not be here. I blew that one. That should not be there. Okay, as I denoted, first I'm going to bring over C2 V2. C1 V1 just stayed on the right hand side. Okay, sorry about that. So let me just put this back anyways and make a little change. This will be C3 V3 over C3, and this will be C2 V2, and this will be C3 V3. Okay, so now I can write V1 just using W1, V2, V3 up to Vn. I no longer need V1. For example, we knew that for any vector in V, since S was a basis, I can write that V equals C1 V1 plus C2 V2 plus C3 V3 all the way down to Cn Vn. Well, you know what? Let me use different constants. D. D1, D2 up to Dn. So this is equal to D1 times V1. But V1 is 1 over C1 W1 minus C2 over C1. Should be dividing by C1. I know you all caught that. Over C1 V2 minus C3 over C1 V3. All the way down to minus Cn over C1 Vn. But that's just D1 V1 plus D2 V2 plus D3 V3 all the way down to Dn Vn. Now we don't need this in the proof, but I think it's important for everyone to see. So that's going to give me D1 over C1 W1. Now V2, we have D2 V sub 2's, and we're taking away C2 over C1. Well, you subtract two constants, you get a constant. Plus V3. We have D3 V3's, and we're taking away C3 over C1 V3's. All the way down to, we have Dn Vn, and we're taking away this number of v sub n's minus cn over c1. That is, and this is v, that is, I'm able to write v using v2, no v1, v2, v3 up to vn, and w1. If I have those n vectors, wonderful. Okay, so what we have at this point is that, okay, so like I said, we didn't need to use this. So let me say it again. Any vector in V can be written using these vectors. So T equaling to W1, V2, V3 up to Vn. So notice when it came to this set, I took out Vn. This spans V. This still spans V. Why? Because I still have V1 in it. V1 is in here. V1 is in here. And if you have V1 and V2 and V3 up to Vn, you span V. V sub 1 is in there. That's very important. And let me just make one slight change. Let's call that T1. Okay. Now we have that T1 spans V. Consider R2 is equal to W1, W2, that's added, V2, V3 up to Vn. So basically I have all of these, W1, V2, V3 up to Vn, and I added W2. Well, this still spans V. This still spans V. Why? Because if this spans V and you add another vector, it's still going to span V. Okay, that still spans V. Okay. Now, just like before, this new vector can be written as C1, V1, C2, V2, up to Cn, Vn. And let me just think for a moment. Yeah, I want to call this W1. Since this set spans V, then using those vectors, W1, V2 up to Vn, I can write a linear combination of those vectors to equal W2. Okay. Now, this is not 0 since W2 is in T and T is linearly independent. That is, W2 can't be 0. And if W2 equals this, then this can't equal 0. Okay. But that implies that at least one CI is not 0. Because again, if all of these were 0, then the sum would be 0, which equals W2. But W2 isn't 0. So at least one of the CIs is not 0. Now, because W2 and W1 are linearly independent, it must be one of the other coefficients that equals 0. Without loss of generality, assume C sub 2 is not 0. So we can solve for V sub 2. We can solve for V sub 2. Bring everything else to the other side. So C2, V2 is equal to what's on the left side minus everything else. C1W1 minus C3V3 minus C4V4 all the way down to CNVN. And 1 times W2. And then we can divide both sides by the non-zero number. C2 is not 0. That's important. Okay, so here it is. V2 is a linear combination of W2, W1, W3, W4, Wn. Hence, T2 equaling W1, W2, remove the V2, V3, V4, that's not a 4, all the way up to V sub n. This spans V. That set spans V. Now, the thing is, we can keep doing this. We can keep doing this. You know, what I can also say is that T2 is a basis. And T1 is a basis for V. The basis for V. It spans V and the set's linearly independent. T1 is a basis for V. T2 is a basis for V. That's important. That's important. Okay, so now that's the whole gist of this theorem or proof. Continuing this process, we see that, and this is the beautiful part, we see that T sub n, which equals to W1, W2, up to Wn, is a basis for V. It's a basis for V. Okay. Now Wn plus 1 is a linear combination of the vectors in Tn. Why? Because this set of n vectors spans V. So if you add another vector, it can be written as a linear combination, which implies that T sub n plus 1 is not a linearly independent set. Hence, let me just go up to the very, very top. K is greater than n. Hence, K is greater than n is not true. K is less than or equal to n. In fact, if K equals n, then T is a basis for V. That is, this set T, if it had exactly n elements, and they're linearly independent, if T is a linearly independent set of vectors in V, and it had n elements, it will be our basis. Just like this set of n vectors is a basis for V. That completes this proof. Hope you all understood it. If you didn't, ask questions. Subscribe to my channel if you like seeing videos like this. Continue watching because that's how you learn. Watch and learn. See you in the next video.